Continuemos.
Hi. AC motor is a founding father of our modern society. Without it, we would fall back. Hi. AC motor is a founding father of our modern
Sí,
society.
de un
Without it,
microondas,
we would
sí,
fall
yo
back to
tuve de
the
esos.
steam engine dark ages. People suffering in cold
Cuidado. ¡Qué susto me di!
wires. Avoid
¡Qué susto me acabo de dar!
the rise of the AC motor. For a long time, AC motor was in hiding until it was recognized by Nikola Tesla and Galileo Ferraris around the same time. Nikola Tesla would prove to be AC's strongest ally. After the civil war between AC and DC, Nikola Tesla triumphed and crowned the AC motor as the king of power in the modern society. That sums it up. I love documentaries. That's why this video is sponsored by Curiosity Stream, with over 2,400 documentaries and non-fiction titles, including exclusive originals. Now, starting at $2.99 a month, you get unlimited access to fantastic documentaries made by some of the world's best filmmakers. You can also get 31 days of free full access if you go to curiositystream.com/electroboom and use promo code electroboom at checkout. So, Nikola Tesla suddenly found a solution to create rotating magnetic fields using three-phase AC. When he was walking with his friend, the solution came to him and he drew it in the sand. And that resulted in two of the most popular AC motors, which are the induction motor and the permanent magnet AC motor. I've talked in detail in one of my previous videos that you can create a rotating magnetic field if you run 3 coils from three-phase AC. Let's start with induction motors, and that's where eddy current comes in, which I talked about in detail in my other video you can watch. Basically, if you pass a changing magnetic field through any conductor, it creates currents inside that conductor called eddy current. As I showed, if you drop a magnet through a copper pipe or a roll of aluminum foil, the magnet slows down. Whee! Beautiful. Whee! It's because the generated eddy currents in the pipe create opposing magnetic fields that push the magnet back up.
No entiendo una
The
mierda.
other way around, the magnet is pushing the pipe down. So if I have a metal pipe, this is brass, and move a magnet beside it, I can move it. There! I think my magnet has to move faster, so I put a bunch of them on my drill bit and I'm gonna turn them fast beside the pipe. Beside the pipe. There you go. Still pretty weak though. Let's try it with a low resistance copper pipe. There you go. This is much faster. So if I have three-phase coils around the metal pipe, which is the rotor, the rotating magnetic fields create the same forces on the rotor and turn it. This is an induction motor because the current is induced in the rotor. It is also an asynchronous motor, meaning that the speed of the rotation is not synchronized by the frequency of the AC power. Like you saw here, the magnetic fields can turn much faster than the rotor. But the rotor at no load can only turn as fast as magnetic fields and not faster. In permanent magnet motors, the rotor is made of magnets. These are synchronous motors, meaning that you can't just drop any AC frequency on the rotor. Imagine this is the rotor and its magnets, and this is the changing magnetic field. If I move the magnet slowly, I can ramp up the speed of the rotor. But if I start fast, the rotor doesn't have time to speed up and follow the fields and doesn't turn. That's why in permanent magnet motors like this, you have to commutate the three-phase AC input frequency accurately. You need to know the position of the rotor and adjust the input voltage frequency, and that becomes more complicated. That's why we need proper control electronics like this electronic control unit or ECU to run the motor. These motors, although they three-phase AC input, always come with these ECUs that run on DC and a control signal. So they're also called brushless DC motors. Let's make an induction motor. To make my three-phase stator windings, I'm using this steel strap and some steel screws and washers. It's important that they are steel or iron so that they can amplify the magnetic fields. Now I just glue the washer to my screw. The washer helps to keep the wires in place. It is fortunate that my screws fit well into my strap holes. I'll put some crazy glue on this too so it won't jump out. Then I'll wind many
Va a
turns
ser
of
una bobina.
magnet wire,
Eso es lo
which
que
is
veo que va.
basically coated copper wire around these screws. The same direction on all screws. You can get these wires from your old transformers. I did 200 turns around this one and should do the same number of turns on the rest too. Hopefully it's enough. Okay, the good thing about these steel straps is that it short circuits the magnetic fields and keeps them strong, the same as the steel body of the motor. Now to keep the wiring simple, I'm gonna do a delta configuration like this. You can do a Y configuration too. For the rotor, I'm gonna use this smoked copper pipe. You probably remember this from one of my super old videos. Let's see if I can weld these two pieces. I'm gonna cut some extra
Lo hizo con aerosol.
piece of this off. This is gonna take forever. I really need to get a vise. I thought copper was easier to cut. This is slightly easier. Now I want to fill this with a whole bunch of steel nails to create an iron core so that the magnetic field has a closed circuit to go through. It is good that the nails are not touching each other because we want the eddy current to only flow through the copper, otherwise the nails would waste energy. They are here only to direct the magnetic field and amplify it. There you go, a rotor with tons of nails in it. Now we take one of these CD covers to make a housing for our motor. Damn it! All my windings are shorted to the chassis. I have to isolate them better. There, I put some paper and tapes between the windings and the chassis and everything is isolated and the rotor is in too. It's finished.
Terminado.
If you recall, I have a three-phase generator here, which is basically a brushless DC motor driving another brushless DC motor, and the output of that one
Veo que
creates three
eso
phases.
va a empezar a ir hasta que revienta.
There. We have three-phase AC signal. Okay, let's see if the motor turns. I control the drive with my function generator. Nothing? Seems like there is no force on the rotor. Maybe more speed? It doesn't work. I guess the problem is the rotor. You know,
Tanto
in
que
real induction
presumía.
motors, there is something called a squirrel cage rotor that creates much more torque due to eddy currents compared to my solid copper. You probably have seen my trusty AC fan, which is an induction motor. See, the rotor looks like a cage. These thicker areas are layers of laminated iron core that pass the magnetic field through, but no eddy current is created through them. But these thinner lines are shorted together and shorted on top and bottom with these metal pieces. An eddy current is created through them that creates magnetic fields that helps the rotor turn. So I have to dismantle this and see if I can change my rotor into a cage. But before that, I like to put some magnet on my rotor and see if the rotating magnetic field actually exists and turn my rotor. I have to make some super light and small rotor. Damn it! With permanent magnet, I just turned it into a synchronous motor. It doesn't work with straight up AC anymore. It just vibrates in place. All you see is just some vibration. Whatever, let's just make the cage. Okay, I made some slots in this thing. I don't know why they do them in an angle, but I'm sure it has something to do with something that you can find in the comments down below. Still, it's not turning at all. Maybe my wiring is wrong. Let me do a Y configuration. It's a bit simpler. Okay, Y configuration and trying one more time. Oh,
Siempre sos pendejo.
Well, I'm done with this. Clearly, I can't make strong enough magnetic fields to make this garbage turn. I mean, look at this tiny piece of copper. Just moving magnets beside it, I can easily move it. I can't make any higher voltage AC out of this thing, and I don't have any more wire to make my winding thicker, so I'm doomed. But at the same time, I thought of something. If instead of my squirrel cage, I put my magnet rotor in there, I should be able to drive it like a brushless DC motor using this ECU. Let's try this rotor. One magnet on each side. Ready? Ah! Look at that! It's turning! Finally something is turning! I made a brushless DC motor, which is basically the same as an AC motor. Tesla would be somewhat proud. And now I'm thinking maybe the ECU can drive my induction rotor. Okay, let's try it. Oh, look at that! I got some movement out of it. Of course, the ECU is not designed to drive the induction motor, but hey, it's moving a little bit. So the magnetic fields are not strong enough for this, but I should be able to run it using my strong magnet. See? This is how it should have turned. So the results are kind of disappointing. I posted a short update video for my patrons at patreon.com and told them how the motor is not working, and I received tons of smart ideas, beside the one that said turn it on and off or call the IT department. For example, increase the voltage to increase the current or run at lower frequency, or increase the number of electromagnets. All good ideas, but I couldn't implement. Increasing the number of electromagnets is something that's very commonly used. For example, if I add another set of three-phase windings and run them from the same AC input, instead of one pair of rotating magnetic fields, I'll have two like this. This creates higher eddy current and more torque, but it also draws double the current from the input. My problem is my AC source, which is this stupid little generator. Initially, I need high currents to create strong magnetic fields and high torque, which this can't provide at low frequencies, because the slower it turns, the lower the output. But if I increase the generator speed, although the output voltage increases, so does the frequency. And you know that the impedance of an inductor is proportional to the frequency. So although the voltage is higher, the current doesn't change much because the impedance is higher. I need an AC source that can provide a lot of current at low frequencies. So I guess I'll have to go and try and design a strong three-phase generator, and then I can talk about more details. In the meantime, you can entertain yourselves using your 31-day free full access and watch some quality documentaries at curiositystream.com/elect